Yes, I'm really pleased to introduce Shaily Rahman. She's an assistant professor now in the Department of Geological Sciences at the University of Colorado in Boulder. She's also an INSTAR Fellow, which INSTAR stands for Institute of Arctic and Alpine Research there. So she's busy in that position now. She, as Laura just mentioned, Shaily was a PhD student here a number of years ago, about 10 years ago now, I believe, time flies. And she was here for a number of years working with Kurt Cochran and myself on silicon-32, which she'll probably mention to you. It's a cosmogenic nuclide. There's about a kilogram on Earth of silicon-32, so it's a really hairy analytical problem to study it. But she conquered that problem and produced some influential research from those studies, as I hope she'll relate to you as we go along. Before that, before she came here, she worked as a radiation waste specialist, I believe, for a number of years after she had received her bachelor's and master's degree from McGill University. And so she has some perspective of the applied aspect of chemistry and energy policies that we have. And I should mention that she went on to do postdocs, one with John Martin at, and not the John Martin of iron fertilization fame, but another one who works on weathering processes in high latitudes in particular. And she worked in Greenland. So that's probably one of our future states. So it's good that I'm just kidding. It's a horrible thing. But anyway, she worked in Greenland, which is a really interesting place. So she has direct experience with high latitude weathering processes and their impacts on the ocean. And she also went on to work with Alan Schiller at University of Southern Mississippi, Stennis Space Center, working on geotraces projects, in particular the chemistry of barium in the ocean, which I don't believe you'll be talking about today. So she is a world expert on the silicon cycle, as I mentioned in my little blurb to you. And so she's going to tell us about that cycle, I think, now, and some of the updates on it. But before I do that, you can read some of Shaily's work recently in this issue of Elements. She has an article on the fate of ocean alkalinity. So that's a real topic of interest now. And maybe she'll tell us today too about how weathering works into that.
Yep, weathering and reverse weathering.
Yep, take it away, Shaily.
Hi, everyone. The last time I was here, I was in this room with this location. I was defending my thesis. So when Bob invited me to give this talk, and I imagined myself here again, I was like, this is going to be really awesome or really triggering or both at the same time. Yeah, I'll let you know how it goes afterwards. But it's been great to be back and see everyone's young faces, Kamazima, and others to see. No one seems to have changed, but I just love this place and all of you students here in the audience, getting a great education. And go talk to people. Okay. Because you've got a lot of expertise in the room, and this is the really fun part before the slog starts. So I'm going to talk to you about the silica cycle. And you know, silicon is the second most abundant element in the Earth's crust. So I'm not going to be talking about the rock cycle. I'm not going to be talking about minerals, not too much. I'm talking about the reactive portion. So this is the part that's mobilized on the surface of our planet, focusing on Earth's surface processes. That's mobilized on our planet. It's a very simple definition, and it moves through different geological, biological, hydrological, atmospheric reservoirs. Okay? So we're talking about silica. When I'm talking about silica, mostly in this context, this is what I'm talking about. So how is silicon mobilized? Well, I'm going to get to that, but just keep in mind that the majority of our rocks, crustal material, silicate, and more than 50% the elements in the periodic table are hosted in silicate rocks and minerals. So if you have a fundamental understanding or some sort of appreciation for how silica is mobilized, deposited, its mass balance, its fluxes, you can use it to inform you about the cycles of a bunch of different elements at the same time. So how is silica mobilized? Well, okay, so this is a time scale of it's a paper in GPC. They were talking about the time scale of forward silicate mineral. Silica is mobilized the surface of our planet through carbonic acid, and it's one of the main controls of atmosphere and our temperature that makes our planet habitable through time. So you have some sort of rock or mineral right there. CO2 in the atmosphere is going to combine with H2O to form carbonic acid. And as that mineral comes in contact with that carbonic acid, it's acidic. So it's going to dissolve part of that rock or mineral, and it's going to release silicon plus a host of cations, plus whatever was in that rock and alkaline. Okay. So something that's really important about how much silicon is released, how much alkalinity is released, in other words, how much CO2 is actually consumed on our planet, you do have to think about weathering congruence. What do I mean by weathering congruency? I mean, like, is that entire rock or mineral completely dissolved? Is it partially dissolved? If you're talking about a rock, is it only certain minerals that are dissolved in that rock and not the rest of the rock? The way that process happens is going to inform this ratio of how much dissolved silicon is released to how much alkalinity is released. In other words, how much silicon is released and how much CO2 is consumed. Okay, so you have different reactions, balanced reactions that can inform that general forward silicate mineral weathering reaction. So as you're thinking about this, the duration of this talk, and maybe later, and maybe this interests you, just keep in mind that sometimes you'll have complete dissolution of a rock, or you might have partial dissolution or secondary phase formation along this flow path. And then you can see that, all of this material is then here sort of rivering, weathering supply. This is the long-term cycle, so it doesn't have a lot of maybe the fluxes that you're used to looking at. It's delivered to the ocean, and then ultimately, the thinking is that you bury some of this, most of this alkalinity as calcium carbonate. So you have this large calcium carbonate burial, and this feeds into this long-term carbon. You also have, of course, some of this net release of CO2 from the ocean. So when we're thinking about this mobilization of reactive silica, some of the things that I think about is how is silica linked to other cycles? Like Bob mentioned barium. How is atmospheric CO2, like specifically thermodynamically and kinetically linked to the reactive silica cycle? And also something that I've started to think about recently is how fast does climate respond to the silicate mineral weathering feedback? And in order to do all of this, we just need to start here and now. We're going to do all of these. Think about these reconstructions through time. We just need to start now and see if our mass balance and fluxes are constrained in the model. Do we have mass balance isotopically, magnitude of silica and other elements in our modern silica cycle? So once it's mobilized, I'm sure if you've taken biological oceanography, chemical oceanography, gone to a beach, silicon can participate in biology. Diatoms, for example, have an obligate requirement for silicic acid, and they're responsible for about 15 to 18% of global primary production. Does anyone know phytoliths? Anyone working? What are phytoliths?
Oh, they're structural parts of plants that are taken up instead of like other structural, like carbon-based structures in plants.
Isn't that so cool? Plants will take up silicon and precipitate amorphous silicon at different quantities and different ratios depending on species. This is also part of like the terrestrial silica cycle. And in the ocean, going back to the marine realm, you know that this amorphous silica phase can act as ballast material. So you're sequestering also in another way. Here's another linkage to carbon, organic carbon from the surface to the deep ocean and the seabed. Now, it's been really interesting to work in this space. There have been so many recent developments. I'm just going to give you a little snapshot of how our thinking on silica mass balances have evolved. So the units here are in teramoles per year. Some of these subscripts are going to stay the same with some of the slides I'm going to show you. So DSI, I mean dissolved silicon, so delivery from rivers, you know, through that weathering mechanism. LTBW is low temperature basalt weathering, so like erosion, weathering of the seafloor. Hydrothermal vents, it's inputs from hydrothermal vents. And then you've got dissolution of that biogenic material once it reaches the seafloor. And with Mollus and Mackenzie, you know, they didn't balance everything, but the balance would have been if we were at steady state, about 15 teramoles per year. So this is 1983. Fast forward 10 years, got the seminal paper by Paul Traeger et al. 1985. And you can see that we've just added a couple of more terms because our understanding of mass balances have evolved. We've got dust input in there. He's also recognizing the burial of coastal biogenic silica in coastal environments. Then you've got this little term right here, RW, reverse weathering, seems to play a really big part in the silica cycle, or so they thought. Now we have a measure of inventory and a residence time of about 15,000 years. So this residence time can be like your measure of overall global reactivity. Okay. What is reverse weathering? Well, if you've taken any of Bob's classes, you're working with Laura, or maybe some others, you already know what it is. And I'm just going to remind you. So there are two ways that biogenic silica can be buried in sediment. Once it reaches sediment, it can just remain unaltered and be this kind of amorphous. This is zooming in on the diatom terrestrial. These photos were supplied by Bob. And it can just remain like this. And you'll have constant deposition on the seabed, and it'll just get buried. And then eventually, maybe over 100,000 year time scale, it'll form chert, or it'll go from opal to opal CT. And to chert. The other way that it can be buried, right at the sediment water interface, is that it can undergo diagenesis. It will undergo diagenic alteration. It can form all of these different phases. You can form an oncogenic alumino-silicate phase, metal oxides, can form little pyrite inside. But generally, the part that I'm going to be talking about is really this formation of this oncogenic alumino-silicate. And when it forms this oncogenic alumino-silicate, the reaction consumes alkalinity and produces CO2. Also consumes a bunch of cations. And if you remember, more than 50% of the elements in the periodic table are hosted in silicate rocks. It seems like it consumes quite a lot of other elements too. So of course aluminum, but then all of these trace elements like lithium, germanium, rare earth elements, manganese, iron. And so general, just kind of kitchen sink reaction mechanism is going to be like you have some sort of amorphous material, okay, calling it BSI. You're going to have some of these main constituents like aluminum and iron, definitely a little bit of magnesium in there too. You've got some cations, major ones like potassium, minor ones like lithium. You need a little bit of organic carbon to set the diagenetic regime, and then you're going to consume alkalinity, producing this new phase that also releases CO2. So this is another coupling between silicon and carbon that has been receiving a lot of attention in the last 10 years, because mostly people thought that this was a minor component of the silica cycle, but now we know that it's a major component, mostly because of the use, a lot because of the use of silicon-32 and really concentrated studies with incubations, a lot of which Bob pioneered. So this is what the you can see it also under microscope, with scanning and spectroscopic techniques where you see this alteration of this diaphragm formation of this flaky amorphous gel-like alumino-silicate in just 6 months. Okay, so already we're talking about processes that are happening much, much faster than 100,000 years. I mean, that's a big difference. Now you're going from something like that's a 5 order of magnitude difference in reactivity right there. Okay, some additional changes to the reactive silica cycle here. Now we're 10 years later. Seems to happen in 10-year steps, though. I think it's ramping up even faster. Triggering the LROSHA 2013, I just want to show you added a submarine groundwater discharge component, and sponges seem to be taking a leading role in the silica cycle. So this is the latest one in 2021. And it's a lot prettier than the box models that I usually got, but it's maybe they're simpler to see. And it's been really interesting to see with ice sheet retreat in high latitude regions, how much siliceous material is actually being delivered to the Arctic Ocean up there. Mostly it's glacial till, and a lot of just meltwater is carrying a lot of DSI. So you've got a lot of continental margin inputs, here's rivers, submarine groundwater discharge. Look at the reverse weathering flux now. It's gone from 0.6 to 4.7. Sponges. You've got like low temperature mineral dissolution. These are hydrothermal vents. And this is like your internal biological cycling plan. And I just want to point out in this new model, we've really tried to highlight the importance of margin process. So all of these processes are happening in the coastal zone. And also your glacial meltwater, a lot of that is happening in the coastal zones, in these large, broad shelves from fjords in high latitude regions. Okay, so when we look at the reactive silica barrier and where it's located, so here you have an ocean, 70% in the Southern Ocean, most of these in continental margins, about 50%. Either as that unaltered biogenic opal or as an alteration product, mostly a reverse weathering product. Okay. You've got some in sponges. Sponges are really cool and interesting. Okay, so there's that silicate mineral weathering coupling to carbon in this long-term model, and I'm just going to add my own little box right there for reverse weathering, which is going to release also CO2 back into the atmosphere. Okay, so it's countering that production. But how much CO2 is it actually releasing? How much alkalinity is it actually consuming? I don't know. I know I have an article on there. It's just based on 3 reactions. I can give you some sort of molar ratio, but this is a wide open field of study. So is anyone looking at ocean alkalinity enhancement? Must have heard of marine carbon dioxide removal strategies, like how do we take carbon out of the atmosphere? A lot of these methods are being deployed in the ocean. But you actually need to, in the coastal, so like you might be seeding the coast with highly reactive minerals. You need to take into account this backward reaction that's actually releasing CO2. They're going to make accurate estimates of how effective that technology is. So that's in the modern. Let me just take you through time. These are going to be busy slides, so I'm going to point out the important parts. Okay. Now, mostly as silica has been modeled, it's only been recently that people have been using coupled silicon to carbon models. And this model, I really like this paper because it has a sediment diagenesis component to it. Okay, I'm not gonna get into the details, all right? But generally, as you look at these figures, this is the modern, is trying to model the Earth state and the ocean state back through 4 billion years. That's a pretty big task. So, you know, big grain of salt here with these models. Okay. And here just putting up this study, this is how the study differs from other studies that didn't have a reverse weathering. Okay, so I'm just going to draw your eye to some of these features. Okay, so the authors came up with a bunch of different models in this paper, or a bunch of different scenarios. Okay, so they kind of came up with this self-consistent silicon to carbon coupled climate model that also had this sediment diagenesis component. And they're saying that reverse weathering warmed Earth's climate by 3 to 6 degrees in the Proterozoic. So here is this change. I'm just pointing the arrows. Here's the modern. Here's the past. Proterozoic's going to go from 541 billion years back to 2.5 billion years. And so it's like this big change might just be due to reverse weathering. Okay. Here you've got the total magnitude of reverse weathering here. Here's your biogenic silica sink. Interesting. Okay, so they're using that. Now they're deriving all of these other parameters. This is how ocean pH changed to atmospheric CO2, continental weathering. What am I missing? Seafloor weathering, outgassing. Oh my gosh. It's a lot. Okay, so just for later, I want to draw your eye to this continental weathering. It's a little under 10 teramoles in the modern, and it's assumed to be about 20 teramoles in the past. Okay, so here's 1 through 6. Okay. Now here's another scenario. This was constrained by some of the estimates, all the estimates that I had in my paper with the work that I did here at Stony Brook. We can see that there isn't much of a difference. Like it's a little bit more buffered when you have when you use that model. Here again, look, big changes in atmospheric CO2, pH, but then you know this continental weathering flux stays kind of steady. One is kind of mapped on top of another. It seems like reverse weathering didn't play much of a role in changing temperature, which means actually that it does play quite a big role in buffering Earth's climate, according to this model. Oh, here's another one. This was constrained by that 2013 paper that I mentioned where reverse weathering started to play a little role. You can see how big of a difference. That's over 10 degrees. That this scenario will play if reverse weathering doesn't play a role in our climate cycle. Okay, but look at these changed. These are big changes. This is a huge jump. That's a lot of heat. So this model, just I want you to understand what it's being tethered by. It's being tethered by these diagenetic model parameters. It's definitely being tethered by whatever molar ratio they're using for silicon to carbon in continental weathering. Also being tethered by the silicon to carbon or CO2 ratio in reverse weathering. And just the magnitude of these sources and sinks, you can think of like fractional percentage of total sinks that's attributed to reverse weathering. The sources and sinks of reactive silica. You can see that as you change all of those fluxes and all of those ratios, you're going to get quite wildly different numbers about how we came to be where we are. You know, it's an existential question. How did the Earth evolve to what it is now? So that we can then maybe use it to predict what it might be in the future. Okay, so I'm going to start showing you a lot of some data using stable silicon isotope ratios. Anyone familiar with the students in the class? Have you come across these isotope ratios? Have you read about them? You have? Whose work? What were you reading about? Oh, my work. Okay. Keep on reading. So you may not be familiar, but you have seen carbon and nitrogen, yes? Isotope ratios, delta N15, delta C13, delta 18 of water, maybe delta 18 of calcium carbonate. Yes? Okay, so some of the same principles will apply. So let me just set the stage for you. So here, in the y-axis, delta silicon 30 is increasing. Now, when you dissolve rocks, and BSC means bulk silicator, when you dissolve rocks, there is no fractionation that we can measure associated with that dissolution. Okay, so you're releasing it at a particular value everywhere. And interestingly, that value for bulk silicate Earth is actually our value that we think is for bulk silicate solar system. So other planets have that same value for their rocks. Isn't that cool? So this delta symbol here is like the difference in values between fluids and solids. So bulk silicate Earth dissolution has a 0 per mil fractionation. But as silicon undergoes precipitation and adsorption reactions, you're going to leave your fluid phase with higher values than your solid phase. Okay. And that fractionation there, depending on what the reaction is, generally roughly has a difference of 1 to 2 per mil. If you're working with sponges or flagellates or really cool other understudied silicifiers, then that fractionation can be up to 6 or 7. They're just really interesting. But generally, that's going to be your distribution. And when you're in pore fluids, I'm going to show you a lot of pore fluid data. If you have forward silicate mineral weathering, you're going to increase your concentration of silicate, and you're going to decrease your delta silicon 30 value. If you have a reverse weathering reaction, generally it's going to consume dissolved silicon, and you're going to increase your delta silicon 30 value. Okay. So forward with dissolution processes like silicate mineral weathering or dissolution of secondary minerals or biogenic silica, you can increase your DSI value and decrease your delta silicon 30. Okay, so try and keep that in mind. So I've shown you 3 or 4 summaries. There are a few more. How can one independently verify some of these summaries? Well, you can use another tool. And another tool that you can use are silicon isotope ratios. Okay. So you can try and see if there's actually a mass balance in your isotopes. Okay, which is what we did. Where we went ahead and we compiled all the available data at that time in all of these different reservoirs. So we've got silicon dissolution. Here's some data from ice sheet meltwaters, groundwaters, this amorphous, highly reactive portion on suspended particulate matter, marine groundwater, riverine BSI, hydrothermal vents, dust. And we compiled all of the distributions in the sinks. So once you have all your sources and once you have all your sinks, do they balance? Here we've got diatoms, radiolaria, sponges. And generally, if you can see this, your distribution is going to be between -2 and +2 generally, unless you're a sponge. And sponges, it goes from -6 to +2. Again, very cool. Okay. So we compiled over 3,000 discrete measurements in various reservoirs. There are more measurements now. So you can just go into the code and keep filling in those Excel sheets that we have and see what you get. Okay. But the other thing that I want to draw your eye to is this green line here is that value of bulk silicon. So when we do this, here is the flux weighted average inputs to the ocean. The median value is about 0.47. Oh, I'm sorry, the sinks. Head backwards. This is the flux weighted average of the sinks. And the sink does not include reverse weathering. So it's just the diatoms, radiolaria, sponges. Here is the flux weighted average of marine sources. The median is 0.62 per mil. Just looking at these distributions, okay, do they look the same? They do not. You can see one is a lot more narrower than the other. So right away, just by looking at this, you can almost predict, I mean, I know they're not in mass balance with the data that we have if you don't include reverse weathering. You can already see where I'm going with this, right? So the distributions of the sinks and sources don't match. The median of the sinks is lower than the sources. And there's a spread into negative values that you just don't see with sources. And it's also not in mass balance with bulk silicate earth, which we know has a particular value. Yeah. So does that mean that it's not in steady state? Does that mean that, you know, you completely messed up manifold processes or how the crust forms or planetary differentiation? We haven't, we just don't have enough measurements on the other side. Okay, so we just need to measure more things. We need to measure more things in more things. So when we try to balance this source and sink term by adding this other component, this reverse weathering component, we're saying, okay, it's going to have that same magnitude that was in my paper, 4.5 teramoles per year, but we don't know what the isotopic distribution is. Okay, so that's the parameter that's varied. So that we can make a prediction, initial prediction of what the composition of that sink needs to be in order to have mass balance. And your budget is likely mass balance. We just don't know where all the sources and sinks are. So here is that sink term. Here is the distribution of diatoms. We just wanted to see if it was different from reverse weathering. And the blue is this distribution for this reverse weathering sink. That's what we're predicting, that solid phase will have that distribution. Okay. So then we went ahead and we tested all of these other summaries. This is just take this in from it. Okay. We tested all of these budgets for both mass balance and silicon isotope imbalance. Some of them looked balanced, but that's because they were missing a lot of terms. And some of them were just clearly not balanced, like here. You can see the distribution is not centered around bulk silicate earth. But the best we could do, it seemed like the 2021 summary approaches mass balance. Okay. So the silica, marine silica budget is balanced at about 15 teramoles per year. Okay. And the other conclusion is that the reverse weathering sinks were quite underestimated in box models prior to 2021. So we've solved the problem, right? No more work to be done. We have the answer. We can go home. Let's pull up that last couple of slides. Okay. The other cool thing that we can do is we can look at how much continental weathering there is by trying to mass balance the sinks on the terrestrials. So remember, violets are a sink, freshwater diatoms are going to be a sink, and pedogenic clays are the secondary base formation. And what's great about this distribution is all of these end members have very different values. Okay. They have very different values. We know that they're sinks because whatever is draining into rivers, this plus 1.2 is very different from bulk silicate earth. So we know that silicon is reacting. Otherwise, the values would be the same. And if we plot them with those end members on these ternary diagrams, most of the simulations for these inverse modeling, there's 10,000 model runs, fail. Until you get to this little area right here. So these are weathering stoichiometry contours, sodium carbon, and these are magnitude of fluxes. Okay, so most of them fail until you get to that narrow area right there. And what we see with this weather incongruency, like this different ratios of silicon to carbon, seems like these are global budgets, right? They're going to be different for whatever drainage basin you're studying. But globally, in these big global ESMs, these Earth system models, type models, your global silicon to CO2 ratio is going to be 1.5 to 1.6. And your continental weathering flux going to be around 20. So if you go back to these scenarios right here in the modern, this is a tether point in this model. They're setting that value equal to about 10. Instead, if you count it at about 19 or 20, it looks like continental weathering didn't really change much through time, which is really interesting in this space because there are all of these ideas about terrestrial land plants, crazy things to our climate system, or the evolution of biogenic silica and diatoms. But maybe, I don't know, maybe we were pretty well buffered. Maybe our Earth temperatures didn't change that much. I don't know. Let's just run some more models. Okay, so another question, is how fast does that sedimentary silica cycle respond? Okay, we're asking these questions about climate and weather. So, silicon-32 is a chronometer. Another way that you can study kinetics generally, if you're doing it in a lab, it's great. You just perturb the system and see how long it takes for the reaction to get back to what you observed at the beginning. How do you perturb an Earth system? You perturb an Earth system with a hurricane. I didn't induce the hurricane, but I certainly took advantage of it. Okay, so now this is something that has naturally mixed up all of your reactants, and you can study how long it takes for that system to return back to the state before the hurricane. And this is all luck. Okay, this is all luck. This is like, instead of started my job in August 2021. And so instead of going to orientation for faculty members where I could learn about health insurance and how do I get my paycheck, I got invited to go out on a cruise. And said, yes, that's what I used my first startup money to do, was to buy a ticket to New Orleans. Dr. Jeffrey Krause, I don't know if any of you work with him, the Dauphin Island. He was on a cruise to study the evolution of silicon and lithium in these areas. And so we happened to sample 13 days before Hurricane Ida, Category 4 hurricane, hit this region, and it made landfall right there. These are the stations that we sampled. Okay. And since then, so it's got this data, and then there's this got a rapid grant to go back out and sample 4 more times. And then Jeff got another grant. Go look at with Brandy Keel Reese to look at microbial interactions. We were supposed to go out. I don't remember the date exactly, but we were stalled because Hurricane Francine hit, which is a Category 2 hurricane. So we had to delay our trip by just a few days, and we were able to get samples 3 and 10 days after a hurricane. We went out in 2025. We were supposed to go out last year. You know what federal funding landscape looked like last year. So we're going out in April 2026, just in 2 weeks from now. So I'm going to show you some data from here. So remember, system is perturbed. How long does it take to get back to its value pre-storm? So I'm making the assumption, and this may or may not be correct, that this is that red line, this pre-storm line is like the starting value. You can see already that in December, that quite a lot of these are profiles from cores. Hopefully you're used to looking at them. Here's depth. On the y-axis, DSI concentration, on the x-axis. You can see that in December, you're almost doubling the maximum for DSI. And then even by August, we thought, okay, in a year, everything's going to go back to normal. Usually people study carbon impacts from hurricanes, and that lasts. So hurricanes induce a bloom, and in 6 weeks you're done, you don't see a hurricane. But your sedimentary silica cycle seems to still be feeling that impact. A year later, we think most people don't have long-term sampling at the same site. So, I'm not sure exactly if this is a seasonal cycle or not. We just have to keep monitoring. So remember this plot. Here's the distribution of the solid phase. So with pore water, which is where the product would be forming, you should have a delta silicon 30 value. You should expect one to range between 2 and 4 per mil. Positive, okay? So let's take a look at some data. These are values in your biogenic phase, your solid phase. Okay, they started around a little over 1. And then they go down to about 0.5. This is very typical. Here's your pre-stored value, and then there it is 1 year later. So the shaded area is like what has been observed. Your average biogenic silica content or value is about like 1 plus or minus 0.7. Okay, so that's that shaded region. So we're right there. That makes sense. What's our pore fluid? These are our pore fluid values in the cessation one. We go up to 4. These are some of the highest measured pore fluid values ever reported. Most pore fluid values, the limited measurements there are around here. So just like we predicted, there is this offset of 1 to 2 per mil in these regions where you just have a lot of reverse weather. And it looks like, in terms of how fast did the system respond, I expected that with doubling the DSI content, we're like, okay, that's a lot of biogenic silica dissolution. Remember, that shouldn't have any fractionation associated with it. I thought all of these values would fall closer to that solid phase material. And it does change it a little bit, but it looks like it's quite positive, which means that a reaction is occurring to make it that way. Okay. So just within a couple of months, your sedimentary silica cycle, you start forming these alumino-silicate phases. It seems like to me. There's a lot of data here that's missing, like we did iron, manganese, sulfur. So we'll plot one on top of the other, but over here, all your iron phases are dissolving, which would be the other big carrier phase, potentially for silicon. So we're very excited about this. And if you do like 2 end member mixing model, here's your coastal value, open seawater value, diatom value. None of your data plot along these lines. So it's not physical mix. That's inducing those isotope ratios, okay? So we can use stable isotope ratios to also perturb a system to see how fast reverse weathering reactions are occurring. Okay, but this is just the start. We just need more measurements of more things. Now we can also use these data to say something. You can use like a model these values. And really what it's going to tell you is something about reactant supply and open and closed system dynamics. So with steady state, you've got a continuous supply of reactants. Rayleigh, you've got a finite or infinite pool. Here is your Rayleigh distillation lines. Here are your steady states. This is your, let's see, where am I? Should be your dissolved, the evolution of your dissolved component, like your pore water. This will be BSI. This is your reverse weathering product or BSI, and here is your quote. Where do the data plot? If you remember, just their range is between 2.5 to 4. So this is all your stable silicon isotopes. When you use these models, you need to have some estimate of how much of your reactant you actually consumed. Now, in other pore water studies, people make an estimate or a guess, or they model it, because we just don't know how much of that DSI is consumed. Well, actually, we do. You need some measure of F. How can you measure this relative proportion of reactants your BSI. Yeah, here's your BSI value, here's your starting value, right here. Oh, right here. How do you get a measure of F? How much of that material has reacted? Huh. I thought I could get a talk out without silicon-32, but I can't. So how much reactant has been consumed? Well, you can add another isotope tracer to see how much of this relative proportion and how much is left in this unaltered phase and how much of it has been altered. Okay, so you can use silicon-32 and you can isolate these phases separately, get the silicon-32 activity in each of them, and you can see what the relative proportions are. And in the Mississippi Delta, it's about 50-50. Okay, so here's my measure of F using silicon-32. Okay, so instead of wondering, okay, is it steady state fractionation or is it really distillation? I mean, there's wiggle here. Can't quite say yet with this system. It would be better if we could be maybe somewhere over here where most of your biogenic silica has been consumed to see whether you're limited by any of these reactants and how fast they're occurring. Okay. But it seems like it's following this Rayleigh distillation line, which means it's limited, it has a limited reactant pool, or your kinetics are quite fast and it's like consuming that reactant pool very rapidly. Okay, so we're doing more of this work. Josie, this slide is for you. You know why? We had our dinner conversation last night. So one of my students, we had a dinosaur party in our department. So we're all dressed as triceratopses, triceratopsi, whatever, however you pronounce it. We're using a lot of samples that Bob collected in French Guiana, the Amazon, and Papua New Guinea. We're using these stable isotope tracers to track this reaction. And the nice thing is that I've already done all the silicon-32 work here. So we have some measure of F. How much has that reaction proceeded? Okay, so just some data from there. What is really interesting about these cores, you got short pores, you got the long pores, and then you've got thin pores that go down. So you just see these different zones where it seems like you have more dominant full reverse weathering reactions, and then in depth, which is a whole other story that we can get to about calcium carbonate that I won't have time at all to get to here. It seems like you go forward, so we keep mineral weather. Just by looking at dissolved silicon and this delta silicon-30. Okay, I'm gonna keep going. Sorry, what time should I stop? Now?
Yeah, maybe like 2 more minutes.
Okay, well, maybe I can go through this a little quickly because this is so fun. So this is part of a project. I got a little seed grant to work with these people. Okay, Stony Brook grad. Stony Brook grad gave a talk here yesterday. He's Stony Brook grad. So, best thing to do with science is work with your friends. You're all great people to work with. They're at NASA. They are looking for water on Mars. Why are they looking for water on Mars? All the things you can do with your degree. Okay, there are all these features on Mars that look like deltaic features. This looks like deltas. Take these on Earth. I'm not sure you'd be able to tell the difference between this and what Iceland looks like, or other braided rivers in high latitude systems. All right. Is there some geochemical component that we can add to see whether there's water on Mars? I just told you a ton of information about water rock interactions. So for silicon to be mobilized, you need to dissolve it. For it to be dissolved, you need water. Precipitates out of water. It'll have a different signature than bulk silicate earth. Okay, so we went to this system, and the Far River, there was a catastrophic outflow in this glacier. It was going in one direction, then in 2029, popped a hole and created this river and went in a different direction. So this river is only 100 years old. And here we're using radium and radon, which I don't have time to get into. This is what I'm focusing on. these violin plots, just notice that surface and groundwaters are different. And when you can use these tracers, you can use this correlation or derive this fractionation along this, I've just sampled along this stream in this river. You can see that the evolution just from calcium to silicon, which can be a measure of secondary weathering, secondary phase formation, evolves. They go from upstream to downstream relations. Concurrent with a linear relationship or correlation between delta silicon 30. And this evolution seems to follow, we're again in this 50% range. You can use calcium to silicon to get at this FSI. So I know where to plot my data. It seems to follow Rayleigh installation, but it could be, we're close enough that it could be steady state. I'm just not sure. We just need more data. The other really interesting thing is that there seems to be quite a lot of secondary mineral formation in groundwater. The groundwater, here's the lake, here's where I sampled. So in less than 100 years, we have both forward silicate mineral weathering, and we seem to be forming secondary phases. And you can read, I know this because I'm combining radium and radon, which is all the work that Joe Tamborski did, to get a time clock for those weathering rates. This was supposed to be my punchline, but I'm so over time. But I'm just going to tell you, like, here are the timescales from radon. That water is in contact with that rock from 3 to 11 days. And you're already both dissolving and precipitating secondary phases. So with the rover, we can tell it, take a sample right here, bring it back. Can't do bulk digestion, can't do bulk characterization. You need to do this fine scale manipulation of that material. Do these leaches, and then it may give you unequivocal evidence supporting the presence of water on Mars. So all of this is really interesting. Like I said, questions, all of everything's been answered. We do have mass balance. We do not have mass balance yet in our summaries. Just last year, I don't know if Garrett is still here. Okay, just work from 2 years ago suggests that the reverse weathering sink might be double what we think it is now. And mineral dissolution might be 4 times higher. So, you know, this is a really fun space to work in, I guess is what I'm saying. It seems to keep evolving. I don't know what's going to happen next. They'll, I don't know, find another silicifier that fractionates by 12 per mil. I don't know, but it's going to be really interesting. Here are my selected conclusions. It's really powerful if you can use both radiogenic and stable isotopes. You can get a lot of information from them, but find the right tool for the job. Rates of reverse weathering from multiple proxies under multiple scenarios. We have quite an abundance of data now that says these happen in really rapid timescales. So I wonder whether everything to preserve mass balance on the surface of our Earth related to reactive silica mobilization and sequestration just happens really fast. This is a really big shift from how we thought things happened in the past when the Earth first formed, we first had oceans, to what's happening now. Terrestrial mobilization and secondary phase formation is also rapid. And we're recommending that for future global climate models, you use silicon to CO2 ratios of 1.5 to 1.6 moles per mole. Thank you. Hopefully I mentioned every minute word, but.
Right, I think we have 2 student questions. Hi, thank you for your talk. It was really interesting and also very relevant to the.
What's your name?
Adrian.
Adrian.
I could you comment more about weather incongruency and like what that depends on?
What weather incongruency depends on? Oh gosh, that's a good question. It depends on quite a lot of things. Like, do you have plants, do not have plants. Do have more physical weathering versus chemical weathering. Like in high latitude systems, we think it's mostly physical weathering. It's a lot of it is subglacial and you just don't have a lot of time that one parcel of water interacts with one grain of material. But just think about what I said, how do I even know that? Like, how can I track one parcel of water and one grain interacting with that parcel of water? In regions like tropical regions like the Amazon, it's going to be mostly chemical weathering and you have a lot of secondary phase formation. But you have regions where, you know, it's raining from Miami, so the slope is quite steep, where you might have physical weathering dominating the section. And then as it gets to less steep regions and you have it spends a lot of time on the floodplain, then it's going to just have more time, that mineral, that phase or those materials to undergo different types of reactions. So it's complicated, but those are some of the primary controls that people are playing with as they think about this system. But in our Earth system, it appears that you have chemical weathering dominating for most places. If you had congruent chemical weathering, it should be able to share plants. Thank you, Adrienne.
Hi, great to my question is about like the model that dates back to the Proterozoic. Obviously, because you mentioned like various residence times and incongruent and congruent weathering, there's like lots of factors that would presumably have changed. And you sort of also suggested that depending on like where the anchor point is, that maybe weather did change or didn't change as much. Do you know how much like different like residence times and like timescales of all those feedback loops, I guess, are factored into that model?
That's I'm not gonna say it. That's a question that I think about quite a lot in terms of timescales of feedback loops. It's all what I like about this paper is that they've laid it all out in the appendices. And those timescales would be implicit in each of the models that they use. So in one of them, they use the Traeger and De La Rocha model, which had a residence time of about 15 to 17,000 years. And in another, they used my data, which would have had a residence time of about 9 to 10,000 years. Traeger et al. In 2021, we have that SGB flux component. That's also part of it, which lowers it down, but the paper came out 1 year before that summary, so they didn't get a chance to use it. So those are some of the timescales that they can use, and there are a lot of calcium carbonate, burial, and release timescales that are in there too. The weathering profiles are probably from uranium thorium disequilibria, and they're long, which is thousands of years, okay? But what the radium and radon data seem to be showing is that this happens on day timescales, like on order of days. So that's a 3 order of magnitude difference. I don't know how that's going to be. I'm not a modeler. I wish I was or knew, or I just work with someone who does a little bit of this. But that would be really interesting. Maybe everything just happens so fast. I don't know. It's fun to think about. I hope that answered your question.
Yeah.
Okay.
Other questions?
Yeah.
You kind of answered my question at the end when you briefly showed some of the newer models or figures by Treadware, where Garrett's doubled values were incorporated. But do you think, aside from what you showed, do you think any other of those sources or sinks like require any revisions in the future?
Oh, right. Rivers are pretty well studied and have been for quite a while, so I feel pretty confident about that estimate. They've been gauged, 60% of world rivers are gauged, and we have concentration data for a number of decades, and we have a pretty good handle on overland water flux. Submarine groundwater discharge is likely going to change. This estimate is only from in the proximal coastal zone from 0 to 50 meters. Because the ocean or kilometers. So you have quite a lot of movement along the shelf, possibly along the sill. We'll have to model it because I don't know what tracer you could use under that scenario. You can't use radium. To get at that fluid flux and that recycling flux, people like Alicia Wilson at USC are trying to model that just using density and heat and wind driven water mass movement. But I expect that part to change. The mineral dissolution is interesting. We've tried, Lizzie Trower and I have tried to balance this. I didn't get a chance to show it. We presented it at AGU with some of these other sinks and nothing balances. Like biogenic silica dissolution can't balance it. Silica flagellates, sponges, none of those three sinks can. I don't remember any more we tried reverse weathering, but I'm not sure that can either because they have such different isotopic compositions, it appears. Your glacial meltwater flux is going to change because, I mean, I don't know what the projection is for ice-free Earth, like when we're going to reach it, but that is going to be, you're going to expose quite a lot of material, and you're going to probably raise sea level by 30 or 40 meters. So all of this is going to change. The river possibly won't. Yeah.
I think we have time for maybe one more question.
Is it really in the ocean changes? Does it change with the rate of reverse temperature?
There's one paper from the Hattle Zone that has looked at this. I would expect it to change because you're just at much colder temperatures and you don't have a lot of organic carbon reaching that depth, and whatever organic carbon does reach it, would probably the gas that it wouldn't be remineralized at as fast a rate as you would get continental slope margin regions, basically shelf margin regions. I just don't remember the results of that. It's like blue et al. 2020. Just Google Hattle Zone reverse weathering. And it should come up. I don't know of another one yet. Do you guys know of a trench reverse weathering? Yeah. Silica cycling, yeah.
Thank you.
It's pretty deep. I think it's in the Mariana Trench.
Right, thank you so much.
Thank
for
you.
a really interesting talk.